Tonight, we're going to drift towards some of the strangest objects in the universe. Black holes. They are invisible. They have no solid surface. And once something passes a certain boundary around them, not even light can return. Some are born when massive stars collapse at the end of their lives. Others sit at the centers of galaxies, so heavy that entire star systems orbit them. Near one, time can pass differently. Light can bend into circles, and the universe can begin to look less like an empty collection of stars, and more like something soft, warped, and deeply strange. So get comfortable. Let the room grow quiet. For the next 2 hours, we're going to slowly explore the calm, impossible world of black holes. There is a black hole so large that, if it replaced our sun, every planet in the solar system would already be inside it. Mercury would be inside it. Earth would be inside it. Jupiter, Saturn, Uranus, Neptune, and even Pluto would all be far beyond the point of no return. This black hole is called TON 618. It is so distant that the light we see from it began its journey more than 10 billion years ago. And yet, even from that impossible distance, it is one of the brightest objects ever observed. Not because the black hole itself is shining. A black hole does not give off light like a star. The light comes from the enormous amount of gas circling around it. Gas falling inward, heating up, glowing so brightly that it can outshine entire galaxies. At its center is a black hole with a mass of roughly 66 billion suns. To picture that number, imagine placing 66 billion copies of our sun into one object. Then imagine that object becoming so compact that it creates a boundary in space where leaving becomes impossible. That boundary around TON 618 is estimated to stretch more than 1,300 times farther from its center than Earth is from the Sun. The orbit of Pluto is only about 40 times farther from the Sun than Earth is. So if TON 618 were sitting where our Sun is now, Pluto would not be near the edge. It would be deep inside, the icy worlds beyond. Pluto would be inside too. Even the outer darkness of the Kuiper belt would be swallowed by the black hole's event horizon. And the strange part is that, from Earth, there might be no dramatic wall waiting for you, no giant black surface, no sudden crash. Space would simply become harder and harder to leave. The deeper you traveled inward, the faster you would need to move to escape, until eventually escape would require moving faster than light, and nothing in the universe can do that. At the edge of TON 618, light itself would lose the ability to travel outward. A beam aimed directly away from the black hole would still fall back in, not because it was pulled backward through space, but because every possible path leading away would curve back toward the center. That is what makes a black hole so strange. It is not just an object sitting in space. It is a place where space has been bent so deeply that the future only leads inward. Even light, the fastest thing we know, cannot find a way out. And TON 618 is so enormous that light would take around 15 days just to travel across the width of its event horizon. 15 days. Just across the darkness surrounding one object. For comparison, sunlight reaches Earth in a little over 8 minutes. So the black hole's shadow alone would be wider than a distance light could cross in 2 full weeks, somewhere in a distant galaxy, far beyond anything we will ever visit. That enormous darkness is still there, quietly feeding, quietly glowing around the edges, holding the mass of billions of suns in a place with no surface, no light, and no way back out, and that is only one black hole. Black holes do not always spend their lives alone. Sometimes two of them find each other. They may begin far apart, orbiting through the darkness like two invisible dancers. For millions or even billions of years, they circle each other from a distance. But every orbit carries away a tiny amount of energy. Not as light, not as heat, but as ripples moving through space itself. These ripples are called gravitational waves. As the black holes lose energy, they slowly move closer together. Their orbit tightens. They speed up. And eventually, the final moments arrive. In a distant galaxy more than 1 billion light-years away, two black holes once began that final spiral. One had about 36 times the mass of our Sun. The other had about 29 times the mass of our Sun. Neither one gave off any light. Neither one could be seen with an ordinary telescope. But as they raced around each other, space itself began to tremble. They moved faster and faster, dozens of orbits every second. Then, in less than a second, they collided. For a brief moment, the collision released an unimaginable amount of energy. About 3 times the mass of our Sun was transformed into gravitational waves, not destroyed, not burned away, turned into motion within space itself. For that instant, the collision released more power through gravitational waves than all the stars in the observable universe release as light. And yet, nothing flashed across the sky. There was no explosion that anyone could have watched from far away. There was no giant fireball. There was only a disturbance moving silently through the universe. A quiet wave in the shape of space and time. It traveled outward in every direction, across empty regions between galaxies, past stars that would never know it had gone by, through clouds of dust, through the darkness between solar systems. And more than 1 billion years later, that wave reached Earth. On September 14th, 2015, it passed through our planet. It passed through oceans, through mountains, through cities, through every person alive at the time. But nobody felt it. The effect was far too small. As the wave moved through Earth, it stretched space in one direction and squeezed it in another. The change was smaller than anything a human body could notice. Smaller than an atom, smaller even than the width of a proton. But scientists had built an instrument sensitive enough to detect it. 2 enormous observatories in the United States, called LIGO, used laser beams traveling through long tunnels. As the gravitational wave passed through, the distances inside those tunnels changed by an almost impossible amount. And for the first time in human history, we directly detected 2 black holes merging. We did not see them. We did not photograph them. We did not hear a sound moving through space. But the signal could be translated into sound. It became a short, rising chirp, a low tone becoming higher and higher. The final signal of 2 black holes spiraling together, colliding, and becoming one. After the merger, the new black hole did not become perfectly still right away. For a brief moment, the warped space around it continued to settle. In a way, the black hole rang, not like a bell made of metal, not with sound, but with tiny waves moving outward through space. Then the ripples faded. The new black hole became quiet, and somewhere far away, in a galaxy we may never see clearly, one invisible object remained where 2 had once been. A black hole with the mass of roughly 62 suns. The collision was over in less than a second, but its final whisper traveled through the universe for more than 1 billion years. And eventually, it reached us. At the center of the Milky Way, there is a star that races around an invisible object at more than 15 million miles per hour. The star is called S2, and every 16 years, it completes one enormous orbit around the supermassive black hole at the heart of our galaxy. That black hole is called Sagittarius A star. It has the mass of about 4 million suns. But S2 does not orbit it from a safe and comfortable distance. At its closest point, the star passes less than 20 billion kilometers from the black hole. That may sound far away, but in space, it is incredibly close. It is only a little farther from the black hole than Neptune is from our Sun. And as S2 reaches that closest point, it moves at nearly 3% of the speed of light. For a brief part of its journey, it is one of the fastest stars we have ever watched. Imagine standing on a planet orbiting that star. For most of the 16-year journey, the black hole would be a distant, invisible force somewhere in the dark. But as the star fell deeper toward the center of the Milky Way, the sky around you would begin to feel different. The pull of the black hole would grow stronger. The star would accelerate. And the rest of the universe would appear to shift in subtle ways. Because near a black hole, gravity does not only pull on matter, it affects time. The deeper you move into a strong gravitational field, the more slowly time passes compared with someone far away. Not enough for a person riding on S2 to notice. A clock beside you would still seem perfectly normal. Your heartbeat would feel normal. A single second would still feel like a single second. But from far away, the light leaving the star would change. As S2 passed close to Sagittarius A star, astronomers on Earth saw that light become slightly redder. This is called gravitational redshift. The light had to climb away from the black hole's gravity before beginning its long journey toward us. And that climb took energy from the light itself. The result was tiny. But it was real. It was one more sign that space and time near a black hole do not behave the way they do here. S2 has been watched for decades. Astronomers have followed its path carefully, year after year, watching a bright point of light move through one of the most crowded and chaotic regions in the sky. They could not see the black hole directly at first. They could only see what the black hole was doing to the star. And the motion of S2 gave them something extraordinary. The star was not simply moving in a perfect repeating oval. Its orbit was slowly turning. Each time S2 completes its 16-year journey, the shape of its path shifts slightly. It does not return to exactly the same orbit it followed before. Instead, the orbit slowly rotates around the black hole. This is something Isaac Newton's view of gravity cannot fully explain. But it is exactly the kind of motion Einstein predicted. Space near Sagittarius A star is warped, and S2 is moving through that warped space. So every 16 years, this one star traces a faint, glowing loop around the darkness at the center of our galaxy. It is like watching a single firefly circle an invisible mountain. The mountain cannot be seen. It has no surface. It gives off almost no light, but its presence is written into every turn the star makes. And for us, 26,000 light-years away, S2 has become one of the clearest reminders that black holes are not just ideas hidden inside equations. They are real. They are nearby, at least by galactic standards. And even now, while the Milky Way turns quietly through space, that star is still making its long journey around the darkness at the center of our galaxy. There is a place around a spinning black hole where standing still is impossible. Not difficult, not dangerous, impossible. There is no wind there, no solid surface moving beneath your feet, no visible current pulling you along. And yet, once you enter this strange region, you cannot remain still compared with the rest of the universe. You have to move. You have to circle in the same direction as the black holes spin. This region is called the ergosphere. It exists outside the event horizon, which means escape is still possible. But inside the ergosphere, space itself is being dragged around the black hole. A black hole can spin, not like a planet with a surface, not like a basketball turning through empty space. A black hole has no solid outer shell, but it can carry something called angular momentum. It can inherit that motion from the star that created it. It can gain more spin by pulling in gas, and it can be spun up again when it merges with another black hole. As it turns, it does something deeply strange. It twists the space around it. Imagine placing a spoon into a cup of coffee and slowly stirring. At first, the spoon moves through the liquid, but keep stirring, and the coffee begins to turn with it. The liquid close to the spoon moves fastest. The liquid farther away moves more slowly. Around a spinning black hole, there is no liquid. There is only space, but the effect is strangely similar. The black hole's spin drags the space nearest to it around in the same direction. Far away, the effect is almost too small to notice. But close to the black hole, the twisting becomes extreme. Space begins to behave less like a motionless stage, and more like a river flowing around a dark object. Outside the ergosphere, you could point your spacecraft in any direction and remain still if your engines were strong enough. Inside it, that option disappears. You could still move outward. You could still escape, but you could not hover in place. You could not move in the opposite direction hard enough to cancel the motion of space itself. Every path through time would carry you slightly forward around the spinning black hole. It would be like trying to stand still in a river that has become faster than you could ever swim against. The river is not made of water. It is made of space. And the black hole is not simply pulling you through it. The black hole has made the space around it begin to turn. This effect is called frame dragging. It was predicted by Einstein's theory of general relativity more than a century ago. The idea sounds almost impossible at first. Most of us imagine space as empty, a quiet backdrop where planets, stars, and galaxies move around. But near a spinning black hole, space is not just sitting there. It has shape. It can bend. It can twist. And it can carry things along with it. The ergosphere is not perfectly round. It bulges outward around the black hole's equator. From a distance, it would have a shape somewhat like a flattened football wrapped around the event horizon. The faster the black hole spins, the more powerful the effect becomes. And inside that strange spinning region, the usual rules of direction begin to change. You could still aim a spaceship outward. You could still try to leave. But even while escaping, you would be carried around the black hole's rotation. There would be no true stillness. No way to pause above one point and look down. The universe itself would be moving beneath you. Scientists believe that this twisting can affect the hot disks of gas around black holes as well. A disk of gas may not always sit perfectly flat. Sometimes the inner part can become tilted. And when it gets close enough to a spinning black hole, the twisted space around it can make that inner flow slowly wobble. It can precess. That means it turns the way a spinning top slowly changes the direction of its axis. Astronomers cannot see this motion directly with their eyes. The black hole is too far away. The region is too small, but they can see changes in the X-rays coming from gas near the black hole. In one system called H1743-322, astronomers observed a repeating pattern that took only a few seconds. The light from the disk changed in a way that suggested the inner flow was wobbling. As it moved, it lit up different sides of the surrounding disk. One side of the disk was moving toward us. The other side was moving away. That changed the light in a rhythm, shifting it slightly from blue to red and back again. It was one of the strongest pieces of evidence that a spinning black hole can truly drag nearby space around with it. And there is something even stranger hidden inside this idea. The ergosphere may allow a black hole's rotation to give energy back to the outside universe. In theory, an object could enter the ergosphere, break apart, and send one piece into the black hole. The other piece could escape with more energy than the original object had. The extra energy would come from the black hole's spin. It would be like taking a tiny amount of motion from the black hole itself. This is called the Penrose process. It is difficult to imagine in any real human sense. But it means a black hole is not only a place where things fall inward. A spinning black hole can also be a source of enormous energy. Some of the most powerful jets in the universe may be connected to this same kind of rotational energy. Narrow beams of particles can shoot away from the regions around black holes at nearly the speed of light. They can travel for thousands, sometimes millions of light years. And at the center of many of those systems may be a spinning darkness, twisting space and feeding energy into the universe around it. So when we imagine a black hole, it is easy to picture something perfectly still. A silent, dark sphere sitting at the center of everything. But many black holes may be spinning. And when they spin, the darkness around them is not still at all. Space begins to turn. Time begins to lean. And close enough to the black hole, the idea of standing still quietly disappears. Somewhere in the Milky Way, a black hole may be moving quietly through the darkness right now. No star is orbiting it. No glowing disk of gas is giving it away. No telescope can simply point toward it and see it. It is alone, a dark remnant of a star that died long ago, drifting between the other stars of our galaxy. Astronomers think there could be millions of black holes like this moving through the Milky Way. Most of them may never be found, not because they are too far away, but because they give off almost nothing. A black hole does not shine. It does not reflect sunlight. And if it is not feeding on gas or pulling material from a nearby star, it can move through space in almost complete silence. For a long time, astronomers mostly found black holes in pairs. A black hole would orbit a normal star. Gas from that star could fall toward the black hole, heat up, and give off X-rays. The black hole itself would still be dark. but the material around it would reveal that something invisible was there. A wandering black hole has no such clue. It may be completely alone, and that makes it one of the hardest things in the universe to find. But in 2011, astronomers noticed something unusual. A distant star near the crowded center of the Milky Way slowly became brighter. Then, over time, it faded back to normal. At first, that might not sound very strange. Stars can change in brightness for many reasons. But this star was not changing by itself. Something invisible had passed between it and Earth. That object did not block the star's light. Instead, it bent the light around itself. The black hole's gravity warped the space between us and the distant star. And for a while, that warped space acted like a giant invisible magnifying glass. The star behind it appeared brighter. Not because the star had become more powerful, not because it had moved closer, but because an unseen black hole had briefly focused its light toward us. This is called gravitational microlensing, and it is one of the strangest ways we have ever found something. Astronomers did not see the black hole. They saw a star changing because the black hole happened to pass in front of it. The brightening lasted for months. Then the star returned to normal. But the story was not over. The black hole had also caused the star's apparent position in the sky to shift by an almost unbelievably tiny amount. The shift was about 1 milliarc second. That is roughly like seeing the width of a quarter from all the way across the United States. By measuring that tiny movement over several years, astronomers could estimate the mass of the invisible object. One research team calculated that it was about 7 times the mass of our Sun. Yet it produced no light at all. It was not a normal star. It was not a white dwarf, and it was too massive to comfortably fit what we would expect from most neutron stars. The best explanation was a black hole about 5,000 light-years away, moving alone through our galaxy. It was estimated to be traveling at around 100,000 miles per hour. That may sound fast, but in the Milky Way, it is simply another quiet traveler. It may have been kicked into motion when the massive star that created it exploded long ago. A supernova is not always perfectly even. One side can push harder than the other. And when the star's core collapses into a black hole, that new black hole can be sent moving through the galaxy like a cannonball released into the dark. It may travel for millions of years, passing through regions of empty space, passing near stars that never notice it, crossing through clouds of gas and dust, never making a sound, never leaving a trail. And unless it happens to line up with a distant star from our point of view, it may remain invisible forever. That is what makes these wandering black holes so eerie. They are not all waiting at the centers of galaxies. They are not all locked in pairs with bright stars. Some may be moving through the same galaxy as us, completely alone. A dark object with the mass of several suns, passing silently through the endless space between stars. And for almost all of human history, we would never have known it was there. A black hole does not always swallow a star whole. Sometimes a star gets close enough to be pulled apart first. Not crushed, not exploded, stretched. Imagine a star drifting through the center of a galaxy. For billions of years, it may have followed a safe path around the dark object at the galaxy's core. Then, after one unlucky change in its orbit, It passes too close. The side of the star facing the black hole feels a stronger pull than the side facing away. At first, the difference is small, but as the star falls closer, that difference becomes stronger and stronger. The black hole begins pulling harder on one side of the star than the other, and eventually, the star can no longer hold itself together. It is stretched into a long stream of hot gas. Astronomers call this a tidal disruption event. It is sometimes called spaghettification, but the name almost makes it sound too simple. This is not a solid object being pulled into noodles. It is an entire star, a sphere of burning plasma, possibly larger than our sun, being pulled into a glowing ribbon by gravity. For a moment, the stream can wrap around the black hole. Some of the star's material is thrown back out into space. Some of it continues falling inward. And as that gas circles closer and closer to the black hole, it begins to collide with itself. It heats up. It glows. It can release flashes of ultraviolet light, X-rays, and other forms of radiation bright enough for telescopes across the universe to notice. A galaxy that seemed quiet can suddenly develop a new point of light near its center. Not because a new star appeared, but because one of its stars was being destroyed. The strange thing is that the black hole itself still remains invisible. It does not light up. It does not become bright like a fire. What we see is the last violent glow of material trying to orbit it. The star is gone, but for weeks, months, or sometimes longer, its remains can keep circling through the darkness. Each loop carries the gas closer. Each collision gives off more energy, and slowly the black hole feeds. From far away there is no sound. There is no visible shockwave spreading through the galaxy. Just a bright flare in a place that had once looked empty. A distant signal telling us that a star wandered too close to something it could never see. And there is another strange detail. A black hole does not need to be enormous to do this. In fact, for some of the largest black holes, the event horizon is so wide that a star may cross it before being torn apart in a way the rest of the universe can observe. The star would disappear behind the boundary before its final light could escape. But around smaller supermassive black holes, the destruction can happen outside the point of no return. That means the universe gets to see the final moments. Not directly. Not in the way we could watch a planet through a telescope, but through the light released by the star's broken remains. Some tidal disruption events have even revealed something stranger. The star does not always die the first time. In a few cases, astronomers have seen repeating flares from a galaxy's center. A star may pass close to a black hole, lose part of itself, escape, and return again later. Each return strips away more material. Each close pass produces another burst of light, like a star being slowly peeled apart, one orbit at a time. Somewhere in the universe, this may be happening right now. A star may be making its final orbit around a black hole. It may not know what is waiting ahead. It may still look perfectly normal from a distance. But as it falls closer, gravity will begin pulling unevenly across its surface. Its shape will stretch. Its outer layers will begin to loosen. And eventually, its light will become part of a glowing stream circling the darkness. For a brief time, that dying star may shine more clearly than it ever did in life. Not because it became stronger, but because it got too close to a black hole. Imagine that without an explosion or a warning, the sun was replaced by a black hole. The same mass would still be there, but the bright yellow sphere in the sky would be gone. For a little more than 8 minutes, nobody on Earth would know. The last light from the sun would still be traveling toward us. Daylight would continue. The sky would still be blue. Then, all at once, the final sunlight would arrive. And after that, there would be no sunrise, no warm glow over the horizon, no sunlight reaching the oceans, the cities, or the moon. Just a black hole at the center of the solar system. But Earth would not fall in. It would not begin spiraling toward the darkness. Its orbit would not suddenly collapse. In fact, Earth would continue moving around that black hole, almost exactly as it moves around the sun now. 1 year would still take 1 year. The planets would continue following their familiar paths. The moon would continue orbiting Earth. Nothing would be pulled out of place. That sounds wrong at first. A black hole is supposed to have impossible gravity. It is supposed to pull in everything around it. But a black hole with the same mass as the sun would pull on Earth with the same strength as the sun does now. From where Earth is, about 93 million miles away, gravity does not care whether the mass is spread across a glowing star or compressed into a black hole. It only cares how much mass is there. The sun has enough mass to hold Earth in orbit. A black hole with the same mass would have exactly the same ability. The difference would be its size. The sun is enormous. You could fit more than 1 million Earths inside it. But a black hole with the sun's mass would be unbelievably small. Its event horizon would be only about 6 kilometers across, a dark circle smaller than many cities. The entire mass of the sun, compressed into something roughly the length of a long highway drive. And from Earth, it would be completely invisible. There would be no bright disk, no flames, no surface to look at. Just empty darkness where the sun used to be. For the planets, life would continue in a strangely normal way. Mercury would keep racing around the center of the solar system. Venus would continue its slow, glowing orbit. Earth would keep moving forward at the same speed it always has. Mars would still follow behind. Jupiter and Saturn would continue circling in the far cold. From a distance, the solar system would still have its shape, but it would slowly become a much darker place. Without sunlight, Earth would begin losing heat. The first changes would feel almost ordinary. Nights would become colder, then days would stop bringing warmth back. The surface of the oceans would eventually begin to freeze. Plants would no longer have sunlight. The sky would grow darker than any night we have ever known. But even then, Earth would not be falling. It would still be orbiting, still moving through space at nearly the same speed, still held in place by the same amount of gravity. That is one of the strangest things about black holes. They are not cosmic vacuum cleaners. They do not reach out across space and pull in everything nearby. A black hole only becomes truly dangerous when you get very close to it. Close enough that its mass is packed into such a tiny region that the pull changes dramatically from one side of you to the other. Far away, a black hole can be surprisingly ordinary. If the sun became a black hole with the same mass, you could even imagine standing on Earth and watching the other planets continue their old paths. Nothing would be racing inward. Nothing would be swallowed. The solar system would simply be orbiting a point of darkness. And in a strange way, the black hole would be harder to hit than the sun ever was. The sun is huge. It fills a massive region of space. A spacecraft aimed toward it has an enormous target. But the black hole left behind would be only a few kilometers wide. It would be like replacing the largest object in the solar system with a tiny invisible mark at its center. You would need to travel directly toward it to ever get close. And if you stayed where you are, moving around it from a safe distance, its gravity would feel familiar. The same pull, the same orbit, the same quiet path through space. There would be no great collapse, no sudden spiral into darkness. Just a world that keeps circling, year after year, around something it can never see. A black point where the sun used to be, and a sky that never becomes morning again. Black holes seem like the closest thing the universe has to forever. They can outlive stars. They can survive the death of entire galaxies. They can sit in the darkness for longer than almost anything else we know. But according to one of the strangest predictions in physics, even a black hole may not last forever. It may slowly disappear, not by exploding like a star, not by being torn apart, but by leaking away, almost unimaginably slowly, into empty space. This idea is called Hawking radiation. It was proposed by physicist Stephen Hawking in the 1970s. At first, it sounded impossible. A black hole is defined by the fact that nothing can escape once it crosses the event horizon. Not matter, not light, not any signal that could carry information back out. So how could a black hole possibly lose anything at all? The answer comes from the strange rules of quantum physics. On very small scales, empty space is not truly empty. Even in the darkest region between galaxies, the universe is never perfectly still. Quantum fields are always present. Tiny fluctuations are always happening. They are too small and too brief for us to see in ordinary life. But near the edge of a black hole, those quiet fluctuations may behave in a very unusual way. According to Hawking's prediction, the black hole's event horizon can cause a faint stream of radiation to escape into space. From far away, it would look as though the black hole was giving off a tiny amount of heat. Not much heat. For a black hole with the mass of our Sun, the temperature would be only a few hundred millionths of a degree above absolute zero. That is colder than almost anything we can imagine. Colder than the dark space between galaxies. Colder than the faint leftover glow of the Big Bang that fills the universe today. And because it is so cold, a normal black hole would be almost impossible to detect this way. Its Hawking radiation would be unbelievably weak. So weak that the black hole would absorb more energy from the universe around it than it would lose. But the universe is expanding. Over unimaginably long stretches of time, the background glow of space should become colder and weaker. Stars will burn out. Galaxies will grow dark. The last pockets of gas will become harder to find. And eventually, if the universe continues expanding for long enough, black holes may have almost nothing left to absorb. At that point, they would begin to lose more energy than they gain. Very slowly, they would shrink. A black hole with the mass of our Sun would not disappear any time remotely close to now. Its lifetime is estimated to be around 1, followed by 64 zeros years. That is so long that the current age of the universe almost stops feeling like a meaningful comparison. The universe is about 13.5 billion years old. A solar mass black hole could survive for a number of years, so enormous that every star we know, every galaxy we can see, and every memory of the night sky as it exists today would be long gone before it had lost much of its mass at all. And larger black holes would last even longer. The giant black holes at the centers of galaxies could remain after their galaxies themselves have faded into darkness. They may become some of the final large objects left in the universe, quiet, invisible, drifting through a future so old that there may be almost no light anywhere. But there is another strange part. As a black hole loses mass, it does not cool down. It gets hotter. A smaller black hole gives off more Hawking radiation than a larger one. So for most of its life, the evaporation would be painfully slow. Almost nothing would seem to happen. But near the end, the black hole would shrink faster. Its temperature would rise. Its faint radiation would become stronger. And in the final moment, according to the theory, it could vanish in a brief flash of energy. A black hole that had lasted longer than stars, longer than galaxies, and longer than almost everything else in the cosmos, would finally be gone. No surface left behind, no dark sphere, no empty hole hanging in space, just radiation moving outward into an even older universe. There is something strangely gentle about that idea. Black holes are often imagined as endings, places where things disappear, places where light cannot return. But Hawking's prediction suggests that even they are only temporary. Given enough time, the universe may outlast its darkest objects. And one day, far beyond any future we can picture, the last black hole may not be swallowed by anything at all. It may simply fade away. A black hole can make the universe behind it appear in front of you. Imagine looking toward a black hole, floating against a field of distant stars. At first, you might expect it to look like a perfectly dark circle, blocking the stars behind it. And it would. But around that darkness, something much stranger would appear. A thin ring of light. Not light coming from the black hole. Light from stars that are actually behind it. Normally, that light would travel away from you. It would miss your eyes completely. But near a black hole, space is curved so deeply that light can be forced to bend around it. A beam of starlight can travel toward the black hole, curve around its edge, and then continue outward in your direction. So a star hidden behind the black hole could still become visible. Its light would be wrapped around the darkness like a halo. The black hole would act like a gravitational lens, not made from glass, not made from mirrors, just a region where space has been bent so intensely that light no longer follows the straight paths we are used to. And the closer the light passes to the black hole, the stranger the view becomes. There is a region around a black hole where light can curve so sharply that it can travel almost all the way around it. In some cases, light can circle the black hole once before escaping. Other rays can circle it twice. Some can make 3 loops, or more. Each extra trip makes the image fainter. Each extra loop creates another thin layer of light around the black hole's shadow. So the bright ring around a black hole is not always one simple ring. It can contain many overlapping images. Some light may have come almost directly toward you. Some may have been bent around one side. Some may have crossed behind the black hole, wrapped around it, and only then found its way to your eyes. It means that near a black hole, one object can appear in more than one place at the same time. A star behind the black hole may form a glowing circle around it. A cloud of gas can look like it has been stretched into an arc. the distant sky can become warped and folded around a dark center. And if a black hole had a bright disk of gas around it, the view could become even more unreal. A normal disk is flat. From the side, you would expect it to look like a thin, glowing line. But around a black hole, the far side of the disk can be bent upward into view. Light from behind the black hole can curve over the top. Light from below can curve underneath. So instead of seeing only the front edge of the disk, you could see parts of the far side hovering above and below the darkness. It would look as though the black hole had folded the disk around itself. You could be looking at gas behind it, beneath it, and around it all at once. The universe would stop looking flat. Direction would stop feeling simple. Up and down would no longer mean what they normally mean. Even the sky behind the black hole could appear upside down. NASA visualizations of an isolated black hole show that the light from the entire sky can become distorted around its shadow. A band of light directly behind the black hole can become an Einstein ring, surrounding the darkness in a complete circle. Inside that ring, the sky can appear inverted. Stars approaching one side of the black hole may first appear on the opposite side, warped and stretched by gravity before their real position comes into view. It would be like looking at the universe through a lens that does not just magnify things, it rearranges them. And this is not only an idea from simulations. The first image of a black hole showed exactly the kind of shape Einstein's theory predicted. At the center of the galaxy M87, more than 50 million light-years away, astronomers captured a glowing ring surrounding a dark region. The black hole itself was still hidden. What they saw was hot material moving around it, with its light bent by the extreme gravity nearby. The dark center in that image is called the black hole's shadow, and the shadow is larger than the actual event horizon. That is because light that would normally travel toward us can be pulled inward, bent away, or trapped in looping paths around the black hole. The darkness we see is not simply an empty circle with a sharp edge. It is the shape made by missing light, a silhouette created by gravity. One side of the glowing ring can also look brighter than the other. That does not necessarily mean there is more gas on that side. The gas near a black hole can move at enormous speeds. The side moving toward us can appear brighter because its light is boosted by its motion. The side moving away can appear dimmer. So even brightness can become part of the illusion. A black hole does not need to move toward you to make the view strange. It only needs to sit there. Its gravity changes the routes light is allowed to take. And because light is how we see everything in the universe, changing those routes changes the entire shape of the sky. The strangest part is that none of this would make a sound. No giant wave would pass through space. No visible hand would reach out and bend the stars. The black hole would remain completely quiet, but around it, the distant universe would twist into rings, arcs, shadows, and repeated images, a place where you could look directly at darkness and still see the light from everything hiding behind it. Imagine two black holes floating alone in empty space. One was formed when a massive star collapsed at the end of its life. The other formed after an enormous cloud of gas fell inward under its own gravity. Before they became black holes, those two objects would have been completely different. One would have been a burning star, filled with heavy elements, magnetic fields, and violent motion. The other would have been a cold cloud spread across a huge region of space. But after enough time had passed, the two black holes could become almost impossible to tell apart. If they had the same mass, the same spin, and the same electric charge, then, according to the classical laws of gravity, the universe outside them would not be able to see the difference. It would not matter what they were made from. It would not matter how they formed. It would not matter whether they began as a star, a cloud, or the remains of something far stranger. From the outside, they could look exactly the same. This idea is known as the no-hair theorem. It is one of the strangest ideas in black hole physics. The phrase sounds a little silly at first, but it means that a black hole has no extra features for the universe to examine. No markings, no texture, no visible history. No way to look at it and tell what fell in. A normal object can carry an endless amount of detail. A planet has mountains, oceans, and layers of rock. A star has a temperature, a chemical recipe, storms, magnetic fields, and eruptions. Even a single grain of dust has a shape, a history, and a tiny arrangement of atoms that makes it different from every other grain of dust. But a black hole is different. Once something crosses the event horizon, the outside universe loses access to almost all of that detail. Imagine dropping a mountain into a black hole. Then imagine dropping an ocean into another. Then imagine dropping an entire library, filled with every book ever written, into a third. To the black hole itself, those things would not be completely meaningless. They would add mass. They could add spin. They might add a tiny amount of electric charge. But the details that made them mountains, oceans, or books would no longer be visible from outside. The black hole would not display a map of the mountain on its surface. It would not carry the shape of the ocean in its gravity. It would not have pages, words, or memories written around its edge. All of that complexity would disappear behind the event horizon. From far away, the black hole would become simpler than the thing that created it. A black hole may begin in a chaotic way. A massive star can collapse violently. Matter can fall inward unevenly. The newborn black hole may briefly be distorted, spinning and shaking in a complicated way. But according to general relativity, those extra distortions do not last forever. Some of them can be carried away as gravitational waves. The black hole settles down. It becomes smoother, simpler, quieter. Eventually, the outside universe is left with only a few basic numbers. How massive is it? How fast is it spinning? Does it carry electric charge? For the black holes we expect to find in space, electric charge is probably close to zero. Space is full of positive and negative particles, and they tend to cancel out. So in practice, many black holes may be described almost entirely by just two things: mass and spin. That means a black hole at the center of a galaxy may be hiding a history more complicated than anything we can imagine. Over billions of years, it may have swallowed clouds of gas, dying stars, wandering planets, and other black holes. It may contain the remains of countless objects that once had their own shapes, motions, and stories. But from outside, all of that history may be hidden behind one smooth darkness, a number for its mass, a number for its spin, and almost nothing else. It is hard to think of anything else in nature that becomes simpler as it grows. Normally, adding things makes an object more complicated. A pile of rocks has more detail than one rock. A forest has more detail than one tree. A galaxy has more detail than one star. But a black hole can keep swallowing more and more of the universe, while the outside description of it remains strangely short. It may grow heavier, it may spin faster or slower, but it does not grow a visible record of everything it has consumed. In a way, it becomes one of the most secretive objects in existence. And this is where black holes begin to touch one of the deepest mysteries in physics. Because quantum physics does not like the idea that information can truly disappear. In quantum theory, the details of what happened to something are supposed to be preserved somehow. They may become scattered. They may become almost impossible to recover. But they should not simply be erased from reality. A black hole seems to challenge that rule. If a book falls into a black hole, what happens to the information in its pages? If a star falls in, what happens to the information carried by every particle inside it? If the black hole eventually fades away through Hawking radiation, where does all that hidden information go? Scientists still do not have a complete answer. Some ideas suggest the information may be stored in a strange form around the event horizon. Others suggest it may be carried away slowly in the radiation released as the black hole evaporates. Others suggest that our understanding of space, time, and information may have to change in ways we have not discovered yet. But whatever the final answer is, the mystery begins with something deeply strange. A black hole can take an object filled with detail, an object with a shape, a history, and a story, and hide nearly all of it from the rest of the universe. So when we look at a black hole, we are not only looking at darkness, we may be looking at a place where the past has been sealed away. A place where a star can die, a planet can disappear, and an entire history can fall beyond a boundary that refuses to explain what happened next. A black hole can be small compared with the galaxy around it, and still decide what that galaxy becomes. A galaxy may contain hundreds of billions of stars. It may stretch across tens of thousands of light years. It may be filled with gas, dust, planets, and entire solar systems. At its center, there may be one supermassive black hole. From a distance, it seems almost insignificant. A dark object hidden in a galaxy so large that its light can take 100,000 years to cross. But when that black hole begins feeding heavily, it can affect the fate of the entire galaxy. Stars are born from cold clouds of gas. A cloud has to cool enough for gravity to pull it inward. It has to become dense. It has to collapse. And eventually, somewhere inside that collapse, a new star begins to shine. So a galaxy that wants to keep making stars needs cold gas. It needs quiet places where clouds can gather and fall inward. But an active black hole can interrupt that process. When gas falls toward a supermassive black hole, not all of it disappears immediately. Much of it circles around the darkness first. It forms a hot, violent disk. The gas collides. It heats up. It releases huge amounts of energy. And some of that energy does not stay near the black hole. It escapes, sometimes as radiation, sometimes as enormous winds, sometimes as narrow jets that shoot out from opposite sides of the galaxy's center. Those jets and winds can travel far beyond the region around the black hole. They can push into the gas spread throughout the galaxy. They can heat it. They can stir it up. They can sweep parts of it away. And once that gas is too hot or too scattered, it becomes much harder for new stars to form. The black hole does not need to swallow every cloud in the galaxy. It does not need to pull stars into itself. It can change the galaxy simply by making its raw material too warm and too restless to collapse. In a way, the black hole can turn down the galaxy's ability to create new suns. Imagine a galaxy as a giant, quiet factory for stars. Cold gas enters. Gravity gathers it. New stars slowly appear. Then the black hole at the center becomes active. It starts sending energy outward. The gas is heated. The clouds stop settling. The factory begins slowing down. Over millions of years, fewer and fewer new stars are born. Eventually, the galaxy can become quiet, not empty, not dead in the ordinary sense. Its old stars are still there. They continue shining. Planets may still orbit them. But the galaxy stops replacing itself with new generations. The bright blue light of young stars begins to fade. The galaxy grows older, redder, calmer. A place where the future contains fewer new suns than the past. And this can happen because of something at the center that is completely invisible. In one galaxy observed by astronomers, a supermassive black hole was sending out a fast wind from its central region. The wind itself moved at about 1/4 of the speed of light. That fast inner wind crashed into gas farther out in the galaxy. It helped drive a much wider outflow, and that larger outflow was carrying away huge amounts of the cold molecular gas needed to make stars. The black hole was not simply feeding. It was changing the conditions across an entire galaxy. There is something strange about that. A black hole is usually imagined as a place where things fall inward, a place that pulls, a place that traps. But an active black hole can also send energy outward with enough force to change everything around it. It can clear gas away from the center. It can fill giant regions with hot plasma. It can create cavities in the gas between galaxies. It can send jets so far into space that they stretch well beyond the visible width of their host galaxy. And all of it begins near an object that may be smaller than our solar system. This does not happen all the time. Most supermassive black holes are quiet for long stretches of time. Our own black hole, Sagittarius A star, is relatively calm right now. It is not lighting up the Milky Way with giant jets or sweeping away all the gas around us. But galaxies can change. A black hole can become active when fresh gas falls toward it. Galaxy collisions can send huge amounts of material inward. A nearby galaxy can disturb old clouds of gas. And suddenly, the quiet darkness at the center has fuel again. For a while, it becomes one of the brightest things in the universe. That is what a quasar is. Not a special kind of star. Not a galaxy made of light. A quasar is the brilliant region around a supermassive black hole that is feeding so actively it can outshine the rest of its galaxy. From far away, the black hole itself is still invisible. But the material around it can become so bright that it hides the entire galaxy behind it. And while that bright phase is happening, the black hole may be changing the galaxy's future. It may be heating the very gas that would have become the next generation of stars. It may be pushing that gas out into intergalactic space. It may be deciding whether the galaxy stays blue and active or becomes old and quiet. There is a strange balance hidden in all of this. Galaxies help black holes grow by sending gas inward. Black holes can then respond by changing the gas around the galaxy. The galaxy feeds the black hole. The black hole changes the galaxy. And over billions of years, both evolve together. So a supermassive black hole is not only an object at the center of a galaxy. Sometimes it is the galaxy's thermostat, a dark engine that can decide when the creation of new stars begins to slow. And in the deepest silence of space, an invisible object can shape the lives of billions of stars without ever touching a single one. The safest black hole to fall into may be one of the largest. That sounds completely backwards. A black hole with the mass of a star can destroy anything that gets close to it. But a black hole with the mass of 1 billion suns can be strangely gentle at the moment you cross its edge. The reason has to do with size. A small black hole packs its mass into a relatively tiny region of space. As you fall toward it, the pull on your feet becomes much stronger than the pull on your head. That difference is what tears objects apart. It is not only gravity itself that becomes dangerous. It is the unevenness of gravity across your body. Near a small black hole, that unevenness becomes overwhelming before you ever reach the event horizon. You would be stretched and compressed by tidal forces long before crossing the point of no return. But a supermassive black hole has a much wider event horizon. Its mass is enormous, but its boundary can stretch across distances larger than the orbit of planets. At that wide boundary, the difference between gravity at your feet and gravity at your head can be much smaller. The pull is still impossible to escape, but it is more even. So in a perfectly quiet thought experiment, with no hot gas, no radiation, and no debris surrounding the black hole, you could drift toward the event horizon of a giant black hole without feeling any sudden change. Your spacecraft would remain quiet. Your heartbeat would feel normal. Your clock would keep ticking 1 second at a time. There would be no glowing line in space, no wall, no surface, no sound waiting at the edge. The event horizon is not a thing you can touch. It is a boundary in the geometry of space and time, a point beyond which every possible route back outward disappears. From your own point of view, you would simply continue falling. One moment you would be outside, the next moment you would be inside. And you might not know exactly when it happened. Far away, someone watching you would see something very different. They would see your light become weaker and redder. Your movements would appear to slow down. Your signals would take longer and longer to arrive. To them, you would seem to approach the event horizon without ever quite crossing it. But from inside the spacecraft, nothing would feel frozen. Your time would still move forward normally. Your clock would not stop. The strange part is that both views are part of the same universe. The person far away would never receive a final clear image of you crossing the boundary, but you would cross it in a finite amount of your own time. And once you were inside, there would be no engine powerful enough to take you back out. Not because the black hole would drag you backward through some invisible tunnel, but because the direction away from the black hole would no longer be a direction you could reach in the future. Outside the event horizon, you can choose to move toward or away from the black hole. Inside it, moving inward becomes as unavoidable as moving forward through time. You could fire your engines. You could turn your ship around. You could point directly toward the light outside. but every future path would still carry you deeper in. That is one of the strangest things about a black hole. The boundary is not a door that closes behind you. It is a place where the map of what is possible changes. Before crossing it, escape is difficult. After crossing it, escape is no longer part of the future. For a while, inside a giant black hole, you might still have time to look outward. The light from the universe behind you would become distorted. It would appear brighter in some directions and dimmer in others. The stars outside could seem to gather into strange shapes as the black hole bends the paths their light can take. But the view would not last forever. The deeper you fell, the tidal forces would begin growing stronger. The gentle edge would not mean the inside was safe. It would only mean that the first crossing did not destroy you. Eventually, the difference in gravity from one part of your body to another would become too great. The same stretching that would have happened far outside a smaller black hole would begin much farther inside this enormous one. And beyond that point, our current theories stop giving us a complete answer. General relativity tells us that matter continues inward. Quantum physics tells us that nature should not become infinitely simple. But when both theories are needed at the same time, we do not yet know the full story. There may be a singularity. There may be some deeper structure hidden beyond what we understand. There may be physics that no human theory has found yet. But before any of that, there is the strange calm of the crossing, a place where one of the most feared boundaries in the universe could be passed without a sound. Not because black holes are harmless, not because the journey would end well, but because the largest black holes are so vast that their edge can be smoother than the edge of a much smaller one. A black hole can be terrifying because it is small, and it can be terrifying because it is enormous. But in one very strange way, the larger one may give you the gentlest entrance into the dark. Somewhere about 250 million light-years away, a black hole is making a sound. Not a roar, not a rumble, not anything a human ear could ever hear. It is playing one note so low that a single vibration takes almost 10 million years to complete. The note is a B flat, 57 octaves below middle C. That is far below the deepest sound any piano could play, far below the lowest sound a human body could feel. It is so low that compared with human hearing, it is more than 1,000,000 billion times too deep to hear. And yet, it is real. The sound comes from the Perseus galaxy cluster, a vast collection of hundreds of galaxies surrounded by an enormous cloud of incredibly hot gas. Most of space is too empty for sound to travel. Sound needs something to move through. Air, water, metal, anything with particles that can push against each other. The empty space between planets and stars is almost completely silent because there is almost nothing there to carry a pressure wave. But the Perseus cluster is different. Between its galaxies is a huge amount of hot gas. The gas is incredibly thin compared with Earth's atmosphere. But it is still enough for pressure waves to move through it, enough for sound to exist. At the center of that cluster is a supermassive black hole. The black hole itself does not make sound in the way a speaker or an instrument does. It has no surface, no throat, no vibration that could travel outward on its own. But the material around it can become violent. Gas falls toward the black hole. Magnetic fields twist around it, and enormous jets of energetic particles can blast outward from the region near its center. Those jets push into the hot gas surrounding the galaxy. They inflate giant bubbles. Each bubble is enormous. Some are tens of thousands of light years wide. They move outward slowly through the hot gas, pushing it aside. And as those bubbles expand, they create pressure waves. The same basic kind of wave that travels through the air when a drum is struck. The difference is scale. A drum pushes the air around it. The black hole pushes an ocean of gas stretching across a galaxy cluster. The waves move outward through the cluster. Not quickly enough for us to watch them move in real time. Not in a way that would look dramatic from Earth. But over millions of years, they leave faint ripples in the X-ray glow of the gas. Astronomers saw those ripples. They did not hear the sound directly. They saw its shape. The hot gas around the Perseus cluster glows in X-rays, and when pressure waves move through it, they slightly compress the gas in some places and thin it out in others. That creates rings and ripples, like the circles spreading across a pond after something falls into the water. By measuring the distance between those ripples, astronomers could estimate the rhythm of the black hole's activity. The giant bubbles appeared to be created at regular intervals, roughly once every 10 million years. That rhythm creates a frequency, and every repeating frequency can be translated into a musical note. In this case, the note was B-flat, a note 57 octaves below middle C, one cycle every few hundred quadrillion seconds. A sound so slow that all of recorded human history would fit inside a tiny fraction of one vibration. If you could somehow survive in the hot gas near the Perseus cluster, you would not hear a deep hum. You would not hear anything at all. The wave would be too slow. You would be waiting millions of years for a single rise and fall in pressure. It would be less like listening to music, and more like living inside one enormous breath of the universe. For a long time, people said there was no sound in space. And for most of space, that is true. The vacuum between stars is silent. A scream in open space would have nothing to travel through. But the universe is not empty everywhere. Inside galaxy clusters, hot gas stretches between galaxies in enormous glowing clouds. And there, sound can exist, not as something we could hear, but as waves of pressure moving through cosmic gas. The black hole in Perseus has likely been repeating this deep note for an unimaginably long time. Its activity may have continued for billions of years. Each burst creates more cavities. Each cavity sends more pressure waves outward, and those waves carry energy into the cluster around it. The sound is not just a strange cosmic detail. It can help keep the gas in the cluster from cooling too quickly. It can shape the environment around entire galaxies. But before it does any of that, it begins as something almost impossible to picture. An invisible black hole at the center of a galaxy, creating bubbles larger than the Milky Way, sending pressure waves through a cloud of hot gas, and quietly playing a note so deep that the universe itself seems to be moving in slow motion. In 2022, NASA turned those real pressure wave measurements into an audible sound. The original note was far too low for human hearing, so scientists raised it by 57 and 58 octaves. The sound people heard was not fake. It was the real pattern of the cosmic waves, moved into a range our ears could understand. A black hole does not have to scream to be powerful. Sometimes it can whisper. Once every 10 million years. What if the Big Bang was not the beginning of everything? What if it was the beginning of something inside something else? There is a strange idea in physics that sounds almost too strange to take seriously at first. The idea that our universe may exist inside a black hole. Not a black hole floating somewhere inside our own universe. A black hole that formed in another universe. A black hole whose interior became everything we know. The stars, the galaxies, the empty space between them. Even time itself. This is not an established fact. There is no evidence that proves we live inside a black hole. But it is a real speculative idea that some physicists have explored. And it begins with a question that is almost impossible to picture. What happens on the inside of a black hole? From the outside, a black hole can look simple. Matter falls inward. An event horizon forms. And beyond that boundary, no signal can return. But from the inside, the story may be far stranger. According to ordinary general relativity, anything that falls into a black hole continues inward. Eventually, the equations lead toward a place called a singularity, a point where density becomes infinite, a place where our understanding of space and time breaks down. But many physicists do not think infinity is the final answer. They think it is a sign that our current theories have reached their limit. General relativity is excellent at describing gravity on enormous scales. Quantum physics is excellent at describing the smallest parts of nature. But inside a black hole, both are needed at the same time, and we still do not have one complete theory that joins them together. Some ideas suggest that matter may not be crushed into an infinite point at all. Instead, at an extreme density, something unknown may stop the collapse. The crushing inward motion may reverse, not into an explosion in the ordinary sense, but into a kind of bounce. In those models, a collapsing black hole in one universe could create an expanding universe on the inside, a new region of space, a new beginning, a new arrow of time. From the outside, the black hole would remain a black hole. Nothing that entered could return. But on the inside, the collapsing matter might become the beginning of an entirely new cosmos. A universe could be born inside the darkness of another. And that brings us to one of the strangest coincidences in cosmology. If you take a region of the universe based on the current rate of cosmic expansion and calculate how much mass and energy it contains, its size comes out surprisingly close to the size a black hole of that mass would have. It sounds like proof. It sounds as though the universe is sitting right on the edge of becoming a black hole. But it is not that simple. The comparison is based on a special cosmic scale called the Hubble radius. It is not the same thing as the full observable universe. The observable universe reaches much farther away than that, because light has been traveling through an expanding universe for billions of years. The Hubble radius is instead a distance connected to how quickly space is expanding right now. And when physicists calculate the average density needed for a universe to be close to flat, something interesting happens. The equations naturally make the mass inside that Hubble-sized region correspond to a black hole radius of roughly the same scale. It is a real mathematical connection, but it does not mean we are trapped inside a giant black hole. The reason is that a black hole and an expanding universe are not the same kind of place. A normal black hole is a concentrated object. It it forms inside a larger space. It has a center. It has an outside, and its gravity pulls matter toward one particular region. Our universe does not appear to have a center like that. On the largest scales, it looks roughly the same in every direction. Galaxies are not rushing toward one dark point in the middle. Instead, space itself is expanding everywhere. There is also no known outside of the universe. A black hole is usually described as an object inside space. But the universe is not known to be sitting inside a larger empty room. Space is the thing expanding. So the size comparison is not a smoking gun. It is more like a strange reflection. Two very different ideas in physics happen to meet at a similar scale. Still, the black hole universe idea has a haunting kind of logic to it. If a new universe formed inside a black hole, the people living inside it might never be able to see the universe that created them. The event horizon would separate the two forever. Any signal from the parent universe would be cut off. The new universe would have its own space, its own time, its own galaxies, its own history. And from the inside, it might simply look like a universe that began with a hot, dense beginning. A Big Bang. In that picture, the Big Bang would not be the creation of everything from nothing. It would be the beginning of our part of reality. The moment a new universe opened from the collapse of matter somewhere beyond our reach. And then another question appears. If our universe could form inside a black hole, could black holes in our own universe create new universes too? Every black hole might become a kind of cosmic seed. A collapsed star could form a black hole. That black hole could hide an entire expanding universe beyond its horizon. And inside that new universe, stars could form, galaxies could appear, life could emerge, and eventually, new black holes could form there too. A chain of universes, each one hidden inside the darkness of another. It is a beautiful idea, but beauty is not proof. For the theory to become more than a possibility, it would need to predict something we could actually test. A pattern in the oldest light of the universe. A specific shape in the way galaxies are distributed. A feature in space, time, or gravity that ordinary cosmology could not explain as well. So far, we do not have that evidence. The standard picture of the universe, with a hot early beginning, followed by expansion, still explains what we observe extremely well. But the black hole universe idea remains one of the most quietly unsettling possibilities in physics, because it asks us to imagine that the darkest objects in the universe may not only be endings, they may also be beginnings, that somewhere beyond an event horizon, hidden from every telescope and every signal, an entire universe could be opening its eyes for the first time. And if that is possible, then the night sky may not be looking out into emptiness at all. It may be the inside of something much larger than we will ever be able to see. Before there were stars, there may have been black holes. Before galaxies, before planets, before the first atoms had even formed. In the first moments after the Big Bang, the universe was nothing like it is now. There were no suns in the sky, no empty spaces between galaxies, no planets moving through darkness. The entire universe was unbelievably hot, dense, and bright. Matter and energy filled everything. Space itself was expanding rapidly. And inside that newborn universe, there may have been tiny regions that were slightly denser than everything around them. Not huge differences, not entire galaxies collapsing. Just small patches where a little too much matter and energy happened to be gathered together. In the universe we know today, a cloud of gas can collapse and become a star. A massive star can collapse and become a black hole. But in the earliest moments of the universe, there were no stars yet. There was only an ocean of energy and matter, and some scientists think that if one region became dense enough, gravity could have caused it to collapse directly into a black hole. No star needed, no supernova, no long life in the sky, just a dense wrinkle in the newborn universe collapsing into darkness. These are called primordial black holes. Primordial means ancient. It means they would have existed almost from the beginning. And if they are real, they could be older than every star we have ever seen. Older than the Milky Way. Older than the first atoms. They may have been there while the universe was still so hot that light could not travel freely through space. The strange thing is that primordial black holes could come in almost any size. Some models suggest they could be incredibly small, not small in mass, small in physical size. A black hole can contain an enormous amount of mass inside an unbelievably tiny boundary. A primordial black hole could be smaller than an atom, while weighing more than a mountain. It could pass through a region of space completely unnoticed. No glow, no surface, no reflection. Just a tiny region where gravity has become strong enough that light cannot escape. Other primordial black holes may have been much larger. Some may have had the mass of an asteroid. Some may have had the mass of the moon. Some may have had the mass of a star. And in a few more extreme ideas, they may have helped create the first giant black holes at the centers of galaxies. That is one of the reasons scientists are interested in them. The universe has a problem. We have found supermassive black holes in the very early universe. Some existed when the universe was still extremely young, and they are already huge. Millions or even billions of times more massive than our Sun. It is difficult to explain how they grew so large so quickly. A black hole born from a dying star would need time to feed. It would need to pull in gas. It would need to merge with other black holes. But the early universe did not seem to give them much time. So primordial black holes offer a strange possibility. Maybe some black holes did not have to grow from stars at all. Maybe they were already there. Small, dark seeds waiting in the young universe. And as gas began gathering around them, they could have grown faster than ordinary black holes. They could have become the first giant black holes, the dark engines at the centers of the first galaxies. But primordial black holes might be connected to another mystery too. Dark matter. Dark matter is the invisible material that seems to make up most of the mass in galaxies. We cannot see it. It does not shine. It does not reflect light. But we can see its gravity. We can see galaxies rotating as though they contain much more mass than their visible stars and gas can explain. We can see giant clusters of galaxies bending light with invisible gravity. We can see the universe behaving as though there is far more matter out there than we can directly observe. Nobody knows exactly what dark matter is. There are many possible ideas. New particles, new forms of matter, something we have not discovered yet. But primordial black holes are one possibility. If enough of them formed in the first moments of the universe, they could still be out there now. They would be dark. They would be massive. and they would interact mostly through gravity. In other words, they would behave a lot like dark matter. Imagine that the empty darkness around our galaxy is not completely empty. Imagine it is filled with ancient black holes, some as heavy as mountains, some as heavy as asteroids, some perhaps much larger. They would not be orbiting the sun like planets. They would be spread throughout the enormous halo around the Milky Way, moving quietly through space, helping hold our galaxy together, invisible except for the gravity they create. It is a wild idea, but it is not proven. Astronomers have searched for signs of primordial black holes in many different ways. They have looked for tiny changes in starlight. They have looked for unusual gravitational lensing. They have looked for patterns in radiation from the early universe. They have looked for clues in the mergers of black holes detected through gravitational waves. So far, no observation has confirmed that primordial black holes make up all of dark matter. In fact, many possible sizes and populations have been strongly limited by what we do not see. But some possibilities remain open. They may make up a small part of dark matter. They may exist in a narrow range of masses, or they may not exist at all. That uncertainty is part of what makes them so interesting, because primordial black holes would not just be another type of black hole. They would be relics from the beginning. They would be pieces of the universe that survived from a time before stars, before galaxies, before the first light we can see today. Every normal black hole we know has a story. A massive star ran out of fuel. A cloud of gas collapsed. Two black holes merged together. But a primordial black hole would have a different story. It would not be the remnant of anything familiar. It would be a fossil from the first moments of reality. A tiny scar left behind by the universe's earliest chaos. And there is something quietly unsettling about that. The oldest things we usually imagine are stars, ancient galaxies, the faint afterglow of the Big Bang. But if primordial black holes exist, some objects in the universe may have been dark from the beginning. They may have watched the first atoms form. They may have drifted through the first galaxies. They may have passed silently through billions of years of cosmic history without ever producing a single photon. And they may still be out there now, hidden in the darkness between stars, older than almost everything we can see. A black hole can throw a star out of an entire galaxy, not by exploding, not by pulling the star apart, but by using another star as part of a cosmic slingshot. Most stars in the universe do not live alone. Many are born in pairs, two stars orbiting one another through the darkness. They may spend millions of years circling a shared center, held together by their own gravity. From far away, they would look like a single point of light. But up close, they are a tiny private solar system. Two suns locked into an endless dance. Now imagine that pair slowly wandering toward the center of a galaxy. Somewhere ahead is a supermassive black hole. It is invisible. There is no glowing surface to warn them away. No sound. No giant shadow spreading across space. Just a region where gravity becomes stronger and stranger with every passing moment. At first, the two stars continue orbiting each other normally. They are still moving together, still bound, still following the same familiar rhythm they may have shared since the beginning of their lives. But as they pass closer to the black hole, its gravity begins pulling harder on the nearer star than on the farther one. The difference is not important at first. Then it becomes impossible to ignore. The black hole is not simply pulling on the pair as one object. It is reaching into the space between them. And eventually, it can break them apart. One star is pulled onto a new path around the black hole. The other is thrown away, not gently, not slowly, thrown outward at a speed so extreme that it may escape the gravity of the entire galaxy. This is called the Hill's mechanism. It is one of the strangest ways a black hole can affect the universe around it. The black hole does not have to swallow either star. It does not need to touch them. It does not need to destroy them. It only needs to steal the energy that was holding the pair together. The star that passes closer to the black hole loses energy. Its path bends inward. It becomes trapped in a long, stretched-out orbit around the darkness. The other star gains that energy, and suddenly it is moving faster than it ever could have on its own. It becomes a hypervelocity star, a star moving so quickly that the Milky Way may no longer be able to hold on to it. For a star, escaping a galaxy is almost impossible. The Milky Way contains hundreds of billions of stars. All of that mass creates an enormous gravitational pull. Our own sun is moving around the center of the galaxy at more than 500,000 miles per hour. And even that is not fast enough to escape. The sun remains bound to the Milky Way. It will keep circling the galaxy for billions of years. But a star caught in a close encounter with the black hole at the galaxy's center can be accelerated to more than 1,000,000 miles per hour. Fast enough to leave. Fast enough to cross the galaxy's outer regions. Fast enough to enter the dark space between galaxies and never return. Imagine what that journey would feel like from a planet orbiting that star. There would be no sudden explosion, no impact, no great flash in the sky. The star would simply begin following a new path. Its speed through the galaxy would rise. The familiar stars around it would begin drifting behind. The Milky Way would slowly become smaller in the distance, and over millions of years, the entire galaxy could fade into a pale band of light behind it. The star would become a traveler between galaxies, a sun with no home, a solar system moving through a darkness so empty that the nearest stars may be hundreds or thousands of light years away, and the black hole that launched it would remain behind, still invisible, still sitting at the center of the Milky Way, still capable of doing the same thing again. There is something almost cruel about the exchange. Two stars can spend their entire lives together. They can form from the same cloud of gas. They can orbit each other through every stage of their lives. And then, in one close pass near a black hole, their paths can be separated forever. One is captured. One is ejected. One becomes a permanent companion to the black hole. The other becomes one of the fastest stars in the galaxy. The black hole turns their shared orbit into a decision neither star gets to make: stay or leave. And because space is so large, the two stars may never see each other again. The captured star may continue circling the black hole on a long, thin orbit. It may return to the same dark center again and again. The ejected star may keep moving outward for hundreds of millions of years. It may pass through the Milky Way's halo. It may drift beyond the visible edge of our galaxy. It may eventually move through intergalactic space, where the universe is quieter and emptier than almost anywhere else. Astronomers have found stars that appear to be doing exactly this. They are called hypervelocity stars. Some are moving fast enough to escape the Milky Way entirely. When scientists trace their paths backward, some of those paths point toward the crowded, dangerous center of our galaxy, toward the place where a supermassive black hole has been waiting for billions of years. One famous hypervelocity star was found racing through the outskirts of the Milky Way at about 1.6 million miles per hour. It was moving so quickly that it had far more than enough speed to escape the galaxy's gravity. Astronomers think its strange journey may have begun with a close encounter near the galactic center. A black hole may have helped turn it into an exile. And there is another strange possibility. The stars closest to the Milky Way's central black hole may include some of the ones that were not thrown away, the ones that lost the cosmic coin toss. They may be the former companions of hypervelocity stars, one star racing outward into the darkness, the other forced to keep circling the black hole that separated them. So when we look at a star speeding away from the Milky Way, we may not just be looking at a fast-moving object. We may be seeing the final result of a story that began with two stars orbiting one another quietly. A story where one invisible black hole reached into that orbit, pulled it apart, and sent one half of a tiny solar system flying into the space between galaxies. Not every black hole destroys what comes near it. Sometimes it does something even stranger. Sometimes it lets a star escape. Some black holes appear to break one of the most important rules in the universe. They seem to send matter moving faster than light. Not almost as fast. Not just incredibly fast. Faster than light itself. At least that is what it can look like from Earth. Near some black holes, enormous beams of particles can be launched outward from the regions around them. These beams are called jets. They can stretch across thousands, sometimes millions, of light years. They move through space at speeds so close to the speed of light that the difference becomes almost impossible to picture. And when one of those jets happens to be aimed partly toward Earth, something strange happens. It can appear to move faster than light. One of the clearest examples comes from the giant black hole at the center of the galaxy M87. This is the same galaxy where astronomers captured the first image of a black hole's shadow. But far beyond that shadow, the black hole is sending a narrow jet of particles out into space. When astronomers watched part of that jet over several years, they saw a bright feature moving away from the black hole. From our point of view, it appeared to be moving more than 6 times faster than light. 6 times. That should be impossible. Nothing with mass can travel through space faster than light. No particle. No spacecraft, no signal, no information. So how can a black hole create something that looks like it is breaking the rule? The answer is not that the particles are truly faster than light. The answer is that light takes time to reach us. Imagine a bright knot of particles moving through a jet. It is traveling almost directly toward Earth, but also slightly sideways across our view of the sky. At one moment, it gives off a flash of light. That light begins traveling toward us. Then, a little later, the knot has moved much farther forward. It gives off another flash. But because the knot has moved closer to Earth, the second flash has less distance to travel. The second flash is chasing the first one. And because the particle is moving almost as fast as light, it can close much of that gap. So the time between the two flashes reaching us becomes much shorter than the actual time between them. From Earth, the motion looks compressed. The bright knot seems to jump across space much faster than it really did. It is not crossing the universe faster than light. It only appears that way because we are receiving its light in a strange order. The universe has not broken its own rules. It has simply tricked our eyes with distance and time. The particles in the jet are still moving at an extreme speed. In M87, they are moving at more than 99% of the speed of light. That alone is hard enough to imagine. A beam of matter moving so quickly that, in a single second, it could travel around Earth more than 7 times. But because the jet is pointed partly in our direction, the light from that motion arrives in a way that makes it look even faster. It is one of the strangest illusions in all of astronomy, and it only works because the universe is so large. Here on Earth, light moves so quickly that we barely notice the time it takes to cross a room. If someone turns on a lamp, you see it immediately. If lightning flashes across the sky, you see it before you hear the thunder because light reaches you much faster than sound. But in space, distances are so enormous that light becomes part of the story. The moon is far enough away that its light takes a little more than a second to reach us. Sunlight takes more than 8 minutes to arrive at Earth. The light from the nearest star system takes more than 4 years. And the light from M87 has been traveling toward us for more than 50 million years. So when we watch a jet near its black hole, we are not watching it happen right now. We are seeing a message from a distant past, a message carried by light. And sometimes, because the source of that light is moving toward us at nearly the same speed as the message itself, the timing becomes strange. The jet seems to outrun the very light that is showing it to us. But it never truly does. Every photon still moves at the speed of light. Every particle still remains beneath that limit. The illusion is created by the tiny difference in arrival time between one moment and the next. It is a reminder that the universe we see is not always the universe as it is. It is the universe as its light arrives. Every star in the night sky is being seen in the past. Some are only a few years old in our view. Some are thousands of years old. Some distant galaxies are being seen as they were before Earth existed. And the black holes we have explored tonight are even stranger because we cannot see them directly at all. We see the stars they pull on. We see the gas they heat. We see the light they bend. We see the waves they send through space. We see the trails they leave behind. But the black holes themselves remain hidden. Dark centers inside a universe made visible by light. And maybe that is part of why they feel so strange. They are not objects we can truly look at in the ordinary way. They are places where light can disappear, places where time can stretch, places where space can bend so deeply that even the distant universe begins to fold around them. Tonight, we have followed black holes through the centers of galaxies. We have watched them pull stars apart. We have watched them collide. We have watched them send ripples across the universe. We have imagined them wandering alone between stars. We have looked toward the edge of places where the future seems to lead only inward. And after all of that, the universe is still here, quiet, vast, unfinished. Somewhere far above us, Stars are continuing their slow paths through the dark. Galaxies are turning. Black holes are waiting. Light is crossing distances too large to understand all at once. But none of it needs to be solved tonight. You can let the strange parts stay strange. You can let the distant things remain distant. You can let the universe keep its secrets for a little while. For now, there is only the quiet around you. The room is still. The night is here. And somewhere beyond the sky, the black holes continue their silent journeys through the dark. Good night.